I'm going to start with this game. So this is an extensive form game. Player 1 moves first. He chooses between two actions, left and right. And then player 2 moves. And depending on the first guy's choice, he chooses, either on this side or that side. The name of the actions are the same, or the strategies are the same, but the payoffs will be different. So the player 2 has two actions, two available options, S and C, both. And then if he plays S, the game is over. But if he plays C, the game is going to move to the third player. And then the third player is going to choose between U and D. And then the game will be over, whatever player 3 chooses. So in this game, the sort of very standard questions like maybe what are the Nash equilibria, or I'm going to give you a strategy profile and ask if it is a Nash equilibrium, and then what are the subgame perfect Nash equilibrium, and etc., etc. So here in this question, let's start with, first off, the strategies, right? If you're not clear about strategies, to be honest, I don't expect you to be able to clear about Nash, SP anyhow, because the fundamental is the strategy. If it is lacking, well, then the rest cannot be complete anyhow. So here, the player 1's strategy. So he's simple. So don't forget, strategy always a function that maps nodes or information set. All right. Remember, every node is an info set. Just happens to have only one decision node in it. So each node to an action. All right. So if I have one node, that means my strategy is just one node to one action. That's it. So it's going to be a singleton. If I have two nodes, that means my strategies are like doubleton. So what I'm going to do in my first node, what I'm going to do in the second node. If I have 10 decision nodes, that means my strategy is tenfold. All right, so what I'm going to do at every single decision node. That's what strategy will look like. So here, player 1 has only one node, so therefore his strategy is going to be a singleton, right? Well, because he has two available options, that means he has two available strategies. So we're going to call them L and R. What about player 2? Well, player 2 has two decision nodes. So therefore, for each node, we must put some action, right? Or sort of choice. Well, here, because he has two nodes, that means his strategies are doubleton, or tuples. And so, because there are only two options available at each decision node, that means 2 to the power 2, 4 available strategies. And they are something like SS, SC, CC, and CS. All right. So always, to me at least, S is the one on the left side and S on the other side. All right. And SC means basically S here, C here, etc. And then finally, the third player has, yes, he has 3 decision nodes, this and this. But the thing is, both of them are connected with dots. That means they are actually in the same info set, which means player 3 cannot distinguish these decision nodes. So therefore, remember, this time I can't say strategy is from node to action. It is in fact info set to action. And because player 3 has only one info set, his strategies will be singleton, very much like player 1. But obviously the name of the actions or options are different for player 3, and so his strategies are U and D. Okay? So, I can create clearly many strategy profiles, I'm not going to do that. But one question I would like to ask now is like, how many subgames are there in this game? I don't know if you guys watched the videos, so that's sort of the key takeaway in this week's videos, the concept of subgame, all right? So remember, the subgame perfect Nash equilibrium is in fact Nash equilibrium at every subgame, all right? So you must have a strategy profile, and that strategy profile, when we sort of concentrate only on one subgame, so ignore all the other parts of the strategy, only focus on the strategies that are sort of relevant in that subgame. So those strategies should be forming Nash equilibrium. Well, the thing is, if For every subgame this is true, well then we call that strategy profile, subgame perfect Nash equilibrium. So here, therefore, you have to first understand how many subgames we have and where they are. So let's remember the definition of subgame. So subgame basically a part of the game tree starting with a single decision node. All right? It always starts with a single decision node that belongs to some player, and then all the branches that follows this decision node. However, that part of this game tree has some properties. One of them, for example, you cannot. So think of this: the subgame is part of the tree that you can just cut and pull it off. But the thing is, when you sort of cut and pull it off, you are not supposed to break any information set and or any other branches. All right, any branch. So you have to basically pick it. It's more like picking apple. All right, so you're supposed to pick the apple, not the branch of the tree. All right, so each apple, sort of single apple, is sort of a game subgame. Well, here, because subgame must start with a decision node, let's start with this one. Is this a subgame? Meaning, when I pick this part of this game, picking it from this decision node that belongs to player 3, is this really a subgame? Well, not really, because you're going to be breaking this info set. All right, so therefore this part of the game is not a subgame. With exactly the same reasoning, this part of the game is not a subgame either. All right, very well. Let's now sort of move one step up and see if I can sort of create a subgame starting from the second player's decision node, right? So this decision node, can I pull this? When I pull this, like the second guy's decision node and all the branches that follows this decision node, can I do that? Well, when I sort of cut through this second guy's decision node, that's perfect. I'm not really cutting any info set or branch here, but the problem is, when I sort of continue pulling, I will be breaking the information set of player 3. So that means this cannot be a subgame. But exactly the same reason, this cannot be a subgame. So what the heck is happening? Well, in this game, there's only one subgame, which is the game itself, meaning the initial node of player 1, right? It's the game itself. So what does that mean? Remember, subgame perfect Nash equilibrium is a Nash equilibrium of a game, and it is a Nash equilibrium at every subgame of the game. Well, this game has only one subgame, which is the game itself. Therefore, can I conclude the following argument? Subgame perfect Nash equilibrium of this game is equivalent to Nash equilibrium of this game. Is this true? Well, yes, this is true. Once again, why this is true? Because this game, the game has no proper subgame. Remember the definition of proper subgame? It means the subgame that does not start with the initial decision node. All right, so basically the game itself is a subgame, but it's not a proper subgame. So basically, proper subgame should be starting with player 2 in this game or with player 3, but we just argued that there's going to be no subgame starting with player 3's or 2's decision nodes, and hence there's no proper subgame. And because there's no proper subgame, that means there's only one subgame of this game, which is the game itself. And by definition, SPNE, subgame perfect Nash equilibrium, is the Nash equilibrium at every subgame. But there's only one subgame, which is the game itself. And so SPNE and Nash equilibrium are mean exactly the same thing in this game. And so if I want to find SPNE of this game, basically all I have to do is just to find the Nash equilibrium of this game. Question? All right. So how can I find the Nash equilibrium of this game? Well, simple. You can draw the game normal form, right? There are 3 players, so that means there's going to be row player, column player, and then the matrix player. Player 3 is going to be the matrix player. And then find the Nash equilibrium. So that's one way. Alternative is basically, which is what I'm going to do. I'm not going to find all Nash equilibrium, but I'm going to talk about few strategy profiles and check if they're Nash equilibrium or not. Once again, Nash and SPNE are the same thing, so therefore I'm not going to say anything particular to SPNE because again, they mean the same thing. So let's check. So I'm going to generate a random strategy profile. Okay, it's just random. I mean, it's coming out of nowhere. So in fact, I'm going to pick the sort of the first strategies for each player. So L, SS, U. So this is a strategy profile. Why? Well, because the strategy profile tells what each player is going to play. Right? This is the strategy of player 1, strategy of player 2, strategy of player 3. And because there are 3 players, that is a strategy profile for this game. Perfect. So now I can check if this is Nash equilibrium or not. How? Well, I mean, simple. Given the other's strategy, I need to verify if player 1 or 2 or 3 is best responding or not. So let's do it one by one. So let's first look at player 1. So the question is the following: is L best response to SS, U? Well, let's see. So the player 2 is playing S on both. So if you like, you can put arrows. I mean, to be honest, to me, it's easier. And then player 3 is playing U. Where? Well, on both decision nodes, remember? So then, if this player plays L, I mean player 1 playing L, I know that, so utility of, payoff of player 1 if he plays L, given the other's strategy, by the way. I mean, whether the rest of the structure, I mean, you don't really have to write this down. You can say player 1's payoff is 0 if he plays L, all right? And then player 1's payoff is 1 if he plays R, okay? So that is enough for me, okay, for example. Why is that? Well, because I already know what strategy profile you are thinking, and you explicitly tell me sort of the logical exercise you're going to be doing. You're going to be checking whether L is the best response to this. So now I understand that you are fixing the other guy's strategy and then checking if L is giving him a higher payoff or not. Meaning, can he achieve a higher payoff than playing L? And then you are verbally telling me that actually L is worse than playing R. All right? So therefore, not a best response. All right? Or alternatively, so that structure is more than enough. Alternatively, of course, you can say, instead of doing this, U1 LSSU, which is equal to 0, less than U1 RSSU, which is equal to 1. Therefore, L is not a best response. That's another way of sort of stating it. Both of them are okay. But the thing is here, the critical structure you should be having is everything up until this point. That's what's required. So you cannot put this argument without this and expect, this is not a solid argument, all right? However, if you state this without stating this first part, well then that still deserves a full credit. Why is that? Well, because now I can see that you are fixing the other guy's strategy and checking the best response. You see what I mean? So I need to see that you are actually doing this best response business. But once again, so you have to explicitly state that. So here, player 1 is not best responding. So because playing L is going to bring him 0, but playing R is going to bring him 1, which is higher. So what does that mean? That means I don't really need to check the other guy's strategy because player 1 here is violating this concept of best responding. Hence, this is not a Nash equilibrium, nor SPNE. Okay? That's exactly what you should be doing. If you like, you can pick another strategy profile and then, verify if it is Nash or not. However, what I'm going to do is actually I'm going to see if I can find all Nash equilibrium without doing this exercise because it's very long. So there's a shorter way. How is that? Well, this is the shorter way. I mean, short, long, these are all subjective, obviously. But so here's what I'm going to do. I am going to do this best respond business. So what I'm going to do is the following. So case 1, player 3 plays you. Basically, I'm asking the following question. Is there any Nash equilibrium or SPNE in this game where player 3 plays you? Why are you starting with player 3? Well, I mean, good question. I don't know why I start. That's sort of my intuition. Can you start with player 1, meaning case 1, player 1 plays left? I think you can, all right? But the reason, I sort of strongly advise you stick to this one. Why is that? Well, here, although there's not really a subgame with player 3's decision note, player 3 is nevertheless the last moving player, right? And so therefore, I know this is not backward induction. I can't really do backward induction here because once again, for example, here I can't say D is optimal here because D gives player 3 1 payoff, U gives him 0 payoff. So he's going to play D here and he's going to play U here because U gives him 1, D gives him 0. I can't really do this analysis. Why? Well, because playing D here and playing U here is optimal, yes, but the problem is when it comes to player 3, the only thing he will be informed is that it's his time to make a move. And he can't say whether he's here or here. So therefore, he can't say whether he should be playing D or U. So then what is he going to play? You see? So for that reason, you cannot isolate those decision notes. That's the idea of subgame. So the subgame is like I can isolate this game and analyze that part of the game without hurting the entire game itself. You see what I mean? But here, I cannot really isolate those parts of the game. And so I cannot really use this backward induction idea. Nevertheless, though, because player 3 is the last moving player, I think you should start with player 3. So he has 2 available options, right? U or D. So if there is a Nash, it will be either player 3 is playing U or player 3 is playing D, right? There's no other option. It's like when I toss a coin, it's going to be either come up head or tail. So this is case 1. Obviously, that means there should be case 2 where player 3 plays D. Maybe there's going to be another Nash equilibrium there. I don't know. But let's first check this one. So player 3 plays U. So fix that strategy. Remember, the Nash equilibrium means fix everybody's strategy and check if I'm best responding or not. So therefore, once I assume player 3 is going to play U, that means fix that strategy. Now, sort of move upwards and see if player 2, what player 2 is willing to do. So here, remember, player 2 has 2 separate decision notes. So player 2, here, let's analyze this first. Here, if he chooses S, he's going to get 1. If he chooses C, he's going to get 0. Because he knows or he believes that player 3 is going to be playing U. That's the reason why I put this arrow here. Well, obviously 1 is higher than 0, so therefore he's going to go for S. Okay? And then here, he's going to, if he chooses S, he's going to get 1. If he chooses C, he's going to get 2. So obviously he's going to go for C. So you see, I actually sort of realized that the second guy is actually preferring to play S here and C here. All right. Well, now I'm not writing anything yet. I'm just putting arrows. Now let's look at player one. If player one is playing left, he knows, so once I'm basically fixing the second guy is going to play S here. So he's going to get 1. I'm sorry, he's player 1, so he's going to get 0. However, if he plays right, so he believes that he's going to get 1. So it's better than 0. So therefore, he should be going for R. So therefore, I kind of created kind of backward induction. It's not really a backward induction, but kind of backward induction. And I kind of created a strategy profile here. So what is that strategy profile? It says player 1 is going to play R. Player 2 is going to play S here. And then C here. And then player 3 is going to play U. So that seems like a Nash equilibrium. Okay? You can check this, all right? You can, like, when you do a sort of multiplication or addition, you can always verify it, right? So you can also verify this. How so? You actually did, but simple. Fix the other guy's strategy. Is R best response to these two? Well, you just realized, right? R is giving him 1 payoff, L is giving him 0 payoff, given that the others are playing according to S, C, and U. Well, the next question is SC best response? Well, here, given that the player 1 is playing right here, for player 2, it really doesn't matter what he plays, right? And so here for player 2, if he plays S, he's going to get 1. If he plays C, however, because the third guy is playing U, he's going to get 2. So therefore, C is the best response. So SC is the best response. All right? And then finally for player 3, and so you do the exercise, but you can verify that this is a Nash equilibrium.